Thank you very much. It's a pleasure to be here, and I'm very grateful to David and to Joan for the invitation. Let me start by saying that perhaps one of the most beautiful things that we have in life is the gift of giving. Giving something, giving love, giving tenderness, giving advice. But perhaps the most extraordinary of all of them is to give the chance of life to someone else. Just as a matter of interest, how many of you have donated blood to another human being? Wow, you're remarkable. Fantastic. How many are you enrolled in a registry for becoming an unrelated bone marrow donor or stem cell? Wow, very good. How many of you have donated? Well, I will talk a little bit why. And I say it's extraordinary, and to illustrate that, let me start with the story of Lloyd. Lloyd was a very fit young fellow. You see him here running a marathon. That was after he had leukemia, he got transplanted. Before that, he was a goalkeeper, he was a fireman. He said that the ball didn't go in. He always challenged him. I said that was goal, but he said no. But you see him here coming out of a house, and in fact, I couldn't find a photograph that I have from him, almost like Rambo, carrying this little boy in his arms that had leukemia. So he was taken to the hospital, he was supposed to be fired. So he got very sick, he was taken to the hospital, we did the blood test, and we found a lot of leukemic cells, blood cells in his blood, and therefore in the bone marrow. Those cells, leukemic cells, were replacing the normal cells. So he didn't have substantial red cells, he didn't have white cells, he was bleeding, so he practically was going to die with this condition. So what we do with a patient like that, we do chemotherapy, irradiation, and by doing that, we destroy, in theory, most of the tumor cells, if not all of them. The cells that produce the stem cells, the cells that produce the white cells, the red cells. So we cure him of the leukemia, but on the other hand, we empty the bone marrow and we leave him practically with no capacity to produce that, because we also kill the stem cells. We had heard a lot about the stem cells in the last years, and we hear the use and abuse, if we could say, of stem cells, because many people make claims that are still not founded. But as you are sitting here, they play an important role. And a stem cell has the capacity to produce another stem cell. That's the uniqueness of it. As you require, they produce other stem cells. But if, for instance, you go to Mexico, like I did last week, and you go to Mexico City, that is 2,200 meters, the concentration of oxygen is too low there. So I send message to my stem cells through mechanisms that I'm not going to go in detail, and I start to produce red cells, more numbers. So the stem cells differentiate and produce that. If, like coming back, I catch a cold, a bacteria, and I didn't want to use antibiotics because you hear all the inconvenience of it, then you produce the white cells, the neutrophils. But if you get even more nasty virus, like the ones that we hear also, then you produce the specialized cells, the lymphocytes, those ones that are really controlling viral infections and controlling that. So in the case of Lloyd, all this was a problem because he had a lot of stem cells dividing abnormally, to the point that all the other cells that were produced were practically either defective or not substantial enough. So by doing that, we killed the tumor cells, as I say, but then he didn't have red cells, he didn't have capacity to produce white cells or red cells. So what we need to do is to replace those stem cells with another stem cell from potentially a donor. This slide is too heavy. Somebody was asking me, is stem cell transplantation a new procedure? And no, it has been there for more than 50 years. And in fact, you see Donald Thomas receiving the Nobel Prize because he was a pioneer that started stem cell transplantation. And this slide, which is no point to go into detail, is full of cornerstone, substantial contributions that has changed completely the field. We had really learned a lot. But the one that to me was very important is something that happened in London many years ago in 1974. When people started to look for unrelated bone marrow donors. The first transplants were performed with families where related donors was potentially the best way to match. But unfortunately, families are not like that. And genetically, we know that not every sibling is going to be a perfect donor. We have, as you know, the Mendelian laws that allows to have the differentiation of the genes. So we have a family that has a segregation of paternal and maternal genes in a different way. And in this case, as you see, if that girl was the one who had leukemia, practically none of the other brothers was completely matched. If the twins that you see there had leukemia, probably one of them could transplant. So that's a major problem. When we do this sometimes we do this test, we sometimes find this kind of abnormal combinations of genes, and then we have to type the Milky Man or the neighbor next door to understand what happened. So one of the challenges that comes is how we find the donor, how we do that, and do we really have a donor? We talk about donors in a different way. We have the capacity to take these same cells, for instance, we could take the cells from Loy, take his cells and remove the bad cells and put back the autologous cells, the immune system that has been there. But very likely he will have the disease again because we are providing the same immune system that was defective and allow the tumor escape. So we have the syngenic, which is the sibling, and then we have the allogenic, the unrelated donors, those ones like you that are enrolled. That is a story that started with this lady, as I say, in England in 1974. A remarkable lady that, trying to save the life of her son, learned that Anthony was going to die because she didn't have another child. And she came to England, and somebody from Australia, although she was British, and she went there. And somebody said to her, it's impossible. There are no donors. I said, no, someone in the world has to be a perfect match for my son. And the guy said, this doctor said, yeah, potentially, but you may need to find 100,000 or 200,000. He said, well, if that's what I need, I will do. And she went to the pubs, to the church, to the schools, to the streets. You see her on the right, demonstrating outside the house of the Prime Minister in 1974. In fact, she created such confusion and commotion that she was detained by Scotland Yard. The bobbies that you see down there were the ones, and they were the first ones to be enrolled as donors. She had such a power of conviction that she changed the concept that it was possible to save the life of somebody. Thanks to her now, look, there are 28 million donors worldwide. The concept grew up through the years, and now there are many registries, and Anthony Nolan has been a charity that has been inspiring to other registries worldwide. I have traveled all over the world trying to help to establish registries, to help people to establish the principles of doing that. You see now there are 27 millions, over 1 million transplants. I was president of the Society of European Bone Marrow Transplantation, and we celebrated last year over 1 million transplants. A remarkable action that means 1 million patients that otherwise would have died had the chance of life thanks to what Shirley Nolan started. So it's a beautiful story. And many people say, am I going to donate bone? What is going to happen there? So how we donate? We extract bone marrow from the, as you see, the pelvis with a needle. That was the most common one. But now we do it easier. We give to the donor just one drug a couple of days before. That mobilizes the stem cells. You could imagine them as grapes in trees in the bone marrow, inside the bones. And then they circulate, and through this equipment, by gravity, we can concentrate them, put it in a plastic bag that will travel to Brazil, to Australia, wherever is a patient that matches that donor. So also now we can obtain cells from cord blood. The cord blood, the placenta actually contains about 100 ml that is rich in stem cells. So we can use it to give the opportunity of life. And now, as I mentioned, there are over 500,000 cord blood units stored. We have at Anthony Nolan also a cord blood bank. NHSBT has also another cord blood bank in the UK. Coming back to Loy, he fight a lot. And you see him here, and this is something very remarkable. Patients has to help us. If no, things doesn't work. But Loy was fantastic. One of the important issues here is to remember that Loy, for the rest of the life, once he received this graft, is a chimeric. It's a hybrid. It's Loy, but the cells that circulate in his blood are coming from John. And the memory, the immunological memory of John is the one that is going to protect Loy for the rest of the life. The vaccinations that John took are going to be the ones that protect Loy for the rest of the life. Not only that, the cells from the graft the immune system, the competent immune system from John, were the ones who are going to eliminate the tumor cells. They are going to be the ones that are going to remove the last cells and avoid relapse. So that's a perfect story. Now he's so fit that keeps running all over the world. Marathons, last week, the London Marathon helped us to raise over £500,000 through the people who are helping us, among them Lloyd. In fact, I was running the marathon about 6 years ago, and at the end, when I was almost dying, I thought, I think I need like Lloyd a bone marrow transplantation. Unfortunately, not all the cases finish like that. The other side of the coin, when we provide, as we did with Lloyd, a graft that we thought that was going to save the life, can kill the patient. And the next slide is I'm going to show it very quickly, because the condition that we call graft versus host disease, as the immune system of Lloyd protected Lloyd, this time the immune system attacked. And that's graft versus host disease. And that is a protein that we all have in our body. We have, imagine a cell full of trees. These cells are actually a source of proteins that are critical in matching. I don't have time to explain them, but you could imagine that there are over 4,000 of these proteins, and we inherit them in two of each one of them. So the combinations that you can have are larger than the entire global population. That's why we need so many donors, and why matching is almost like it's going to Las Vegas. And we have developed technology that is using like next generation sequencing. Anthony Nolan has introduced the Pacific Bioscience. We call it third generation sequencing, where in one of these microchips, we can actually put DNA from the donor that actually allows to type in detail nowadays the perfect source of matching. Before we couldn't do that, and that was the difference between Lloyd and the case I showed you. We hope that that's going to improve. Also, donation is becoming more simple. So many of you that are donors, I don't know if Anthony Nolan, but we use and have revolutionated. In the past, you used to receive a box with a needle that will tell you, go to your GP. Now, we introduce saliva, so you have a little tube that where you spit and you send it. And it's helping us, as you see here, how far you can spit to save lives. And that has helped us to attract young people, and by doing that, increase the opportunities of saving lives to donors. In fact, Anthony Nolan has changed the age of become a donor between 16 and 30, because we know that donors at that age have better opportunity of providing chances of life. This curve shows you that each one of them is a cross of a patient that unfortunately died. The survival rate still is not as good as we would like. 60% of our patients survive. This is good, because you imagine that 60% is against 0, but still we need to do a lot to increase the numbers to 40%. But donors under 30 makes a big difference. Why? Because patients still relapse. 50% die, and they die because the disease comes back, because there is graft versus host disease, the reaction that I show you, and there is infection. So what we are doing in my institute and in other groups is trying to teach cells, because as we are saying that our immune system is competent and is fighting tremendous infections here. Many of you might have a virus, many of you are cytomegalovirus, about a common virus that normally we keep in control, but in a patient that is infected, that virus can kill the patient. So we are taking cells from healthy donors, teaching them in the lab. I don't have time to go into this, but the idea is to get cells from not just bone marrow, not just stem cells, but take the right cells that will help us to differentiate them into the right cells, the policemen that we need to fight leukemia, the policemen that we need to fight infections. As we were learning, antibiotics are not just a problem, but also expensive. A patient after transplant that get infected costs 50,000 to 70,000 pounds more the treatment of that patient. So if we do just cell therapy, we get cells from healthy donors, so we educate them in vitro in the laboratories and we teach them. I have a grant at the moment from the European community of 6 million. And one of the problems, and it's good to have welcome here, that Anthony Nolan has as a charity is that we don't receive money from, because we are not a university. So we have a problem because we depend on charities, we depend on the European community to get grants, but we have published over 1,200 papers that have been cited over 16,000 times, because we are developing strategies, policemen that we can give to the patient. With no doubt that we are living an exciting time. And we, as a community, a scientific community, we have changed now the way we can actually reactivate cells. We know that, for instance, you take a tumor, a lymphoma, you might see a lot of T cells, those policemen that should kill those cells surrounding it. But the tumor has the capacity to inhibit those T cells. So now we have learned how to reactivate them, how to wake them up. We can also take cells from the donor and change them genetically by adding some other markers that help them to direct them directly to the tumor cells. So I think we are living a very fantastic time. We're revolutionating the immune system by learning how we can actually redirect, reactivate, and recognize bacteria. We can probably, and virus and tumor cells, we may not need transplant. I hope that the case of Lloyd, which is remarkable, because before he received the transplant, we took a sperm from him, and obviously now you see his twins after inseminating his wife. So this is a remarkable case. We want every case to finish like that. And I have the hope that one day we will go to the pharmacy, to the drugstore like we used to get, but now to get the stem cells or lymphocytes or other cells that help us to fight a cold, and we don't have to use antibiotics and everything like that. I think with this one I want to thank you and invite you to become a donor if you are not. Thank you.
Thank you, Alejandro. So it's inspiring to see the human case studies, the people whose lives have been saved. Tell us what's happening now in research. What's exciting you about studies coming out of the lab that show where stem cell transplantation is likely to be going?
So we are trying to, on one hand, trying to improve the patient that receive the graft, because as I say, there are 3 complications. So we are trying to train cells like that. For instance, my institute on this grant that we have is trying to select what we call regulatory cells. As we have cells that protect us and are very good to defend us, we have also other ones that sort of calm them down. In absence of them, we will have autoimmunity or other conditions. So we are taking cells from cord blood that are regulatory, and we are starting a clinical trial to treat patients with graft versus host disease. But the most remarkable probably action that has happened is what is called CAR T cells. We are taking cells from the same patient and loading them with different kind of recognition mechanisms that now are capable to identify tumors. So this is working so well that many patients are treated with no transplant. So they just receive these autologous cells that has been modified, and they have the capacity to kill the tumor.
And the new technologies like CRISPR that allows you to edit genes open new doors?
Absolutely. I think, for instance, one of the ideas will be to match, to allow to, if you don't find the perfect donor, to modify in some ways the cells that you can provide the right graft. Because it's easy to find a donor when you search for a Caucasian individual. Of those 28 million donors, the majority are coming from England, Germany, United States. When we search for a minority patient or for a mixed race, you remember the case of searching for Sarah that was just recently mentioned, all in all the news and everything. And that's the problem that we have. So creating capacity to provide donors to other patients, even if they are coming from all sorts of parts of the world. So that's why the cord blood panel and the cord blood collection has been focused in places at the moment, at least in Anthony Nolan, in King's College, in Birmingham, where we are capable to collect minorities.
Well, it's a pretty strong call for action for all of us to do our bit to grow that registry. Thank you very much, Alejandro Madrigal.
Thank you.